Hi, welcome. My name is Amy and I am the lead mathematics tutor in Pinnacle Coaching. In this series of videos, I would like to take you through some of the core topics in mathematics and extension 1 mathematics in the New South Wales syllabus. So this first one we're going to do is geometric application of calculus and how it relates to curve sketching. So firstly, couple of points. We need to find stationary points, inflection points, intercepts, and using all of that information and put that onto a graph. Before we jump into an example, I would like to just briefly revise the theory behind those 3 points. Firstly, stationary points. Stationary points relates to the gradient of the function, and if you recall, the first derivative f dash x is telling you the gradient of the function. So if your gradient is positive or if your f dash x is positive, you're sloping upwards, negative sloping downwards. If it's equals to 0, stationary. So in other words, there are 2 core things you need to do to find stationary points. Firstly, you need to solve f dash x to 0. Yeah, so looking for the stationary points. Second, you need to do a table of values to test the nature of the stationary points, so whether it's a minimum, maximum, inflection. Now, there are more than one method to find or determine the nature of a stationary point, but I find that with curve sketching it's a lot easier. If you do a table of values, it gives you visuals around what it should look like. Second, inflection points. So inflection relates to the second derivative, and if you recall what the second derivative is the concavity of the function. Okay, so if it's negative, it's concave down. If it's positive, it's concave up. If it's equal to 0, potential inflection point. So that takes us to 2 steps. First one, you want to solve double dash to 0. So just looking for where those potential inflection points are. Second, you need to do a table of values to test around it. So table of values. Because not all potential inflection points actually gives you actual inflection points. An inflection point requires a change in concavity, so going from a concave down to a concave up situation or vice versa. Okay, so once I show you the examples, these will make a lot more sense. And finally, just finding intercepts. So you're looking at x-intercepts and y-intercepts. So x-intercepts, very typical, you just sub y equals 0. So for x, if you're looking for y-intercepts, you then sub in x equals 0. Now you might not actually be always be able to find x-intercepts. It's very dependent on the question itself, but I'll show you examples where you can find x-intercepts and instances where you cannot find x-intercepts. So in this first example, what I'm going to show you is how to address a typical exam question. You can see this is a very typical structure on a curve sketching question. So first we're going to find the stationary points, determine the nature, find the coordinates of the inflection, find any intercepts, and then we're going to use all of that information to sketch. So the first step is to find the stationary points. First we find what f dash x is. So differentiating that, bring the power down, subtract the power by 1, same with this one. So bring the power down, subtract the power by 1. And then that's 4x cubed minus 12x squared. Since usually you then have to solve it to 0, ideally if you can factorize it, factorize it. Okay, which becomes 4x squared, x minus 3. So let's solve f dash x to 0. So we've got 4x squared, x minus 3 equal to 0. Solving each component to 0, you basically get x is 0 and 3. So once you've identified where your stationary values are, the next step is to do a table of values so we can determine the nature. So usually I like it to do the testing in one table as opposed to two, where some teachers do teach that method. I don't like it in two tables because I think it is a little bit confusing. And the thing with one table is that you can see a continuous graph. You can see the continuous shape of this graph. Alright, so in terms of picking values, just pick values that's around the stationary point. So for example, 0, minus 1 and 1 will be good picks. And 1 is actually a very good pick because it's a number in between 0 and 3. And just pick another one above 3, so 4 for example. So pick up your calculator and then determine what these values are. This one is minus 16, minus 8 and 64. So once you've done that, we are just really looking at the sign of the number, not so much the number itself. So this is telling us it's negative sloping, stationary, negative sloping, stationary, positive sloping. That's all you're looking for here. This gives us the shape of the graph, and that's why I really like the first derivative table. Now after that, don't forget to answer the question. Coordinates means you need to give me X and Y coordinates. If the question says determine the nature, you need to tell me what the nature is. So is it a stationary inflection point? Is it a maximum or minimum turning point? You need to explicitly answer the question. Don't leave the examiner hanging. Alright, so how do I find the points first? So put 0 back into the original function so we can identify where it is. So it's at 0, and same with 3. So sub in 3, you get minus 27. Okay? So therefore, answering the question, so therefore, stationary inflection at 0, 0, and minimum turning point at 3 minus 27. And that is it. You've done the first step. So part B, we're now going to look for the inflection points. Remember, the inflection points relates to the second derivative. So we already got the first derivative from before. I'll just quickly rewrite it over here. Second derivative just simply means you differentiate that again. And then simplifying that. And factorize it as well. So once you've done that, solve it to 0. So you get x is equal to 0 and x minus 2 is 0, which gives you 2. Now don't just leave it like that. You then need to test with a table of value to show that there is a change in concavity. So quickly constructing a table here. So we're testing double dash. So minus 1, 1, 3, for example. Okay, so you're putting these numbers into the second derivative to test the concavity. So putting them into the calculator, you should get 36 minus 12 and 36, which tells you you're looking at the sign only. So positive is concave up, negative is concave down, positive is concave up, which is perfect because at each of these points you have a change in concavity happening. And that's the definition of an inflection point. They're both inflection points, and in fact 0 is actually a stationary inflection point because we already shown that in the first part. It's a stationary point. Okay, so therefore, before we do that, let's find the y coordinates. So when it says coordinates, regardless of what it says, just find the coordinates. Yeah, you don't want to miss out on marks just because you're a little bit lazy or you've forgotten to do something so simple. Yeah, very easy marks to get. So F2, putting that into the original function, we're finding the coordinates. That gives you minus 16. So therefore, inflection points at 0, 0, so that's the first one, which we were expecting anyways, and then the second one second one is not a stationary inflection point, just an inflection, and I'll show you the difference when we sketch this. Alright, so next up we're going to find the X and Y intercepts. So how do you find X and Y intercepts? How you normally find it for any other function really. So starting with X intercept, you want to solve Y to 0. So solving that to 0. Factorize, if you could. And then you're solving each component to 0 essentially. So you've got x is 0 and x is equals to 4. So that means we've got two intercepts here, 0, 0 and 4, 0. Now, x-intercepts is not something you can always find with a lot of the exam questions in this area. So generally speaking, I will say if the question does not ask for it, I would not bother with x-intercepts. However, y-intercepts is definitely something you can always find. So all you need to do here is solve x to 0, so you sub x equals 0 in there. So in other words, you're finding out what f0 is, which we actually found like a couple of times by now, which is essentially the same point, okay? So I won't rewrite that as essentially the same point, 0, 0, the origin. Alright, and finally, just putting all the information together. So I've already summarized all the bits we found from performing A, B, and C. So we found, just to summarize, stationary inflection at 0, 0, minimum turning point at 3 minus 27, inflection point at 2 minus 16. So that's the non-stationary one, and the stationary one is up here, and intercepts including the origin as well as 4, 0. So the first step I would do is actually just plot all these key features. So I'll show you what I would do. So 0, 0, 3 minus 27, let's say it's down here, it's never going to be to scale, to be honest with you. I'll come back to this one, I'll do 4, 0 first. Okay, now usually I don't plot in the inflection point until the very last moment, and I'll show you why in one sec. And remember that first derivative table that gave us something like this? That tells you that's the shape of the graph, so use that to help you visualize. So it's telling you here, it's sort of got this stationary inflection feature. And here is our minimum turning point. So you can draw these little, like, I guess, strokes and features to help you piece the entire thing together. Now I'm going to just trace over the features. Okay, I'm just going to clean it up a bit so it doesn't look so messy. Alright, so that's pretty much it. So that gives you the shape of the graph, so your shape should correspond with that, and then I'm just trying to make sure my stationary point looks very stationary, so there's no disputes there. Now, I've deferred the inflection point to the last moment. You usually just sort of look at your graph and roughly dot it, so that's roughly where it changes concavity from concave down to concave up. So I'm just going to go back and label that. And you'll find that non-stationary points are like that. You don't need to specifically emphasize the point. Yeah, it could be very smooth like this one, just changes concavity naturally, okay? And it doesn't really help graphing per se, so that's why I always graph without the inflection. You just draw it first, then you dot it in, and usually there's no issues there. So now that I've showed you an example on how to perform the basic steps, I want you to pause this video and have a go at doing this question yourself. So I've tweaked it slightly. There is a slightly more complicated part in part B, but just give it a go. Try to at least sketch the graph for the domain you're looking at. Just be careful if you're looking for a particular domain, make sure you are finding what f-4 as well as f3 are, so you're actually plotting the endpoints of the domain. So pause the video right now and have a go. Alright, so welcome back. I hope you had a go. Let's go through the answers. So we're trying to graph this function essentially, so I've just copied the function here. So the first step is to differentiate that, you get that, factorizing it, you get that. So solve it to 0, and you get -3 and 1 are your stationary points. So test around those points, I've selected -4, 0, which is in between -3 and 1, and also tested 2. So you can see it's positive sloping, then negative sloping, then positive sloping. So you have a very standard sort of cubic shape here. So that means you've got a maximum turning point at -3, and 16 is the y coordinate. To find the y coordinate, you just sub -3 back into the function. And same with 1. 1 is a minimum turning point, and it's -16. So second part, inflection. So differentiate the first derivative. I suggest you differentiate this line. That's the easiest to do. So differentiate that, you get 6x plus 6, which is taking out the 6, you get 6 times x plus 1. Solve that to 0, -1 is your number. So test around it to show there is a change in concavity here. So there is, it changes from concave down to concave up, meaning there is an inflection point at -1, 0. Again, to get 0, you have to put -1 back into the function. Okay, so now that we've got all the features, how do we sketch this? So just to summarize, what have we got so far? We've got a maximum turning point at -3, 16. And remember we've got a table of values that tells us that's going to be the shape, so keep that in mind. Minimum turning point at 1 -16, inflection at -1, 0. And the question specifically asks us to graph the graph for only in between -4 to 3. So I've looked for the endpoints of the domain as well. So there's -4, 9 as well as 3, 16. So what I'm going to do is just sort of cut off the graph at -4 and 3. So we remember to only sketch for that domain. And I'm just going to plot all the points on first. So I've got -3, 16. So let's say it's roughly here. Okay. 1, -16, so let's say it's roughly here. And then -1, 0, so let's say it's roughly there. Okay, and we've got -4, 9, so slightly below, so let's say here. And this one is at 3, 16, so it should be same level, 3, 16. And what are you trying to do? So that's a maximum, that's a minimum, so you're trying to create that sort of shape across those features. So let's join them together. And that's pretty much it, and that's crossing at -1. In fact, that's an inflection point. Alright, I think that's all you need to illustrate here. The other thing you do need to illustrate, I know the question doesn't actually explicitly ask for it, but always illustrate the y-intercept. Very simple, because you're putting x equals 0 in there. It's just really the constant in the equation, so it's -11. That's where your y-intercept is going to be. So now that we've got the graph, we're going to answer a slightly more challenging question in part D. Part D is an example of the type of questions you'll get to distinguish your top students of your band 6 students versus your low band 6 and band 5 students. So if you can answer that extra mark, it will put you at that much of an advantage. So let's take a look how we answer part D. Alright, so let's take a look at how to answer part D. So in the question it says, draw an appropriate line or otherwise solve this equation. First, you have to relate it to the actual function itself. If you look at the function, it's meant to be -11, but we've got -27. So let's pull that apart. I'll show you how. So -27 is -11 minus 16. And what I'm going to do is move that to the other side. Okay, so your ability to interpret this expression is important, because actually what this means, that's the equation of the function. You're solving the function to 16. So in other words, where are the y values equal to 16? So if you go back to the graph, y equals 16 is here. So that's the line they are referring to, y equals 16. Yeah, so you're solving when the function is equals to 16. It's talking about the horizontal line, y equals 16. And you can see there are two answers here, -3 and 3. And that's your answer. So it's just really an observation from the graph. So So therefore, x is equals to 3 and -3, and you're done. And if you're able to answer this type of questions, that will put you into the band 6 sign as opposed to band 5 students. So band 5 students will be able to do the graph no trouble. It's these type of questions that's going to put you into the top band. So hopefully you found this video helpful. And if you like this video, please like, comment and subscribe. I'll do another segment on maximization and minimization, but if you have any topics at all you would like me to cover, let me know down in the comments below and I'll try to get those videos out to you. Bye for now.